NASA just released images that are forcing the scientific community to question everything. After weeks of silence, after mounting pressure from researchers worldwide, after congressional inquiries and leaked memos, they've finally made public the high-resolution photographs of 3 I-Atlas taken by the Mars Reconnaissance Orbiter. And what these images show is almost impossible to believe. What you're about to see, what the astronomical community is frantically trying to explain, might be the most significant visual evidence we've ever captured of something that shouldn't exist in nature. This is November 10th, 2025, and the images released just hours ago are spreading through scientific networks faster than anyone can contain them. Researchers are analyzing every pixel. Military advisors are being briefed. Government officials are preparing statements. Because these aren't blurry, distant photographs that allow for multiple interpretations, these are crisp, detailed, 30-meter per pixel resolution images that show Atlas in unprecedented clarity. And they reveal structures, patterns, geometries that are challenging every assumption we've held about what this interstellar visitor actually is. Let me be absolutely clear about what we're looking at. The high-rise camera aboard the Mars Reconnaissance Orbiter is one of the most powerful imaging systems humanity has ever placed in space. It was designed to photograph the surface of Mars in extraordinary detail, to identify landing sites, to study geological features, to capture images sharp enough to see individual rocks and boulders. When Atlas passed within observation range of Mars in late October, NASA redirected this incredible instrument to capture images of the mysterious visitor. The images were taken on October 23, 2025, when Atlas was approximately 42 million kilometers from Mars. At that distance, with HiRise's capabilities, the theoretical resolution should allow identification of features as small as 30 meters across on Atlas's surface. That's the length of 3 school buses. That's enough to see real structure, real detail, real evidence of what Atlas is made of and how it's constructed. And what the images show has the scientific community divided between excitement and something approaching fear. The first thing that's immediately apparent is that Atlas is not a simple, irregular rock. The overall shape is cylindrical, elongated, with dimensions that multiple analysts are estimating at roughly 400 meters in length and approximately 120 meters in diameter. But it's not a rough, chaotic, naturally formed cylinder like an asteroid tumbling through space. The shape has regularity. The proportions are consistent along its length. The cross-section appears circular rather than irregular. This is the first problem for the natural object hypothesis. Natural objects in space, comets and asteroids, form through accretion, through gravitational collapse of dust and debris, through impacts and collisions over billions of years. These processes create irregular shapes, lumpy, asymmetric, chaotic forms. There are no perfect cylinders in nature at these scales, no geometric regularity, no smooth proportions, yet Atlas appears to have exactly these characteristics. The immediate response from some scientists is that this could be chance, that from this particular viewing angle, an irregular object might appear more regular than it actually is. But analysts who've examined the light curves, the way Atlas reflects light as it rotates, report that the cylindrical appearance is consistent across multiple orientations. But the shape is just the beginning. When you examine the surface at higher magnification, when you process the images to enhance contrast and bring out subtle features, you see patterns. Linear features running along the length of the cylinder, parallel lines, evenly spaced, extending for hundreds of meters. In engineering, in architecture, in manufactured objects, we see these kinds of patterns constantly. They're the result of construction methods, of modular design, of components assembled in regular ways. In nature, we don't see them. Natural surfaces have fractal complexity, random variation, the signature of chaotic formation processes. The linear features on Atlas are being called seams by some researchers and stress fractures by others. The interpretation depends on what you believe you're looking at. If Atlas is artificial, if it's a manufactured object, these could be the boundaries between hull sections, the places where components connect, the visible evidence of assembly. If Atlas is natural, these would need to be some kind of geological feature, perhaps layering in the original material, perhaps cracks that form during thermal stress or impact events. But here's the problem with the natural explanation. The features are too regular, too parallel, too evenly spaced. Geological processes create patterns, yes, but those patterns have variation, irregularity, the randomness inherent in natural phenomena. These features show precision that's hard to reconcile with natural formation. Some analysts have measured the spacing between the parallel lines and found it consistent to within a few percent across the entire visible surface. That level of regularity is a hallmark of design, of intentional construction, of engineering. There are also what appear to be surface panels or plates, rectangular sections of the surface that seem slightly different in reflectivity or texture from surrounding areas. In the enhanced images, these panels create a grid-like pattern across parts of the cylinder. Again, interpretation is everything. If you're looking for a spacecraft, you see hull plating, armor sections, solar panel arrays, the kind of modular surface design that spacecraft engineers use. If you're looking for a natural object, you need to explain how rectangular sections with different optical properties could form naturally and arrange themselves in regular patterns. The spectroscopic data adds another layer to the mystery. When light reflects off Atlas, the spectrum of that light tells us about the composition of the surface. Different materials absorb and reflect different wavelengths. Ices, rocks, metals, each has a characteristic spectral signature. The spectrum from Atlas is unusual. It doesn't match typical comet compositions, which are dominated by water ice, frozen carbon dioxide, organic compounds. It doesn't match typical asteroid compositions, which are usually silicates, various rock-forming minerals, sometimes with metal content. Atlas's spectrum is flatter than expected, showing relatively uniform reflectivity across visible wavelengths, with some unusual absorption features that don't match known materials well. Some researchers suggest this could indicate a surface covered in fine dust, or regolith, that's been processed by millions of years of cosmic ray exposure, creating an altered layer that doesn't resemble the original composition. Others suggest it could indicate artificial materials, alloys or composites that don't occur naturally, surfaces designed for specific optical properties. The thermal signature is equally puzzling. Infrared observations show that Atlas radiates heat in ways that aren't quite consistent with a passive object just reflecting and absorbing sunlight. There are temperature variations across the surface that suggest internal heat sources or at least thermal regulation. The warmest areas don't correspond perfectly to the parts most directly illuminated by the sun, which is what you'd expect from a simple rock. Instead, there are warm regions in shadow, cool regions in sunlight, a distribution of temperatures that suggests something more complex than passive solar heating. One particularly striking feature visible in multiple images is what some researchers are calling the vent structures. There are roughly circular features, possibly 7 to 9 of them, visible in the photographs, distributed around the circumference of the cylinder. These circular features appear darker than surrounding surface, possibly recessed, possibly openings of some kind. Their size is estimated at 10 to 15 meters in diameter. Their distribution is not random. They're spaced at regular intervals, positioned symmetrically around the cylinder's circumference. If these are the sources of the jets that have been observed optically, if material is being expelled from these openings, then their regular distribution and sizing makes sense from an engineering perspective. Attitude control thrusters, positioned symmetrically around a spacecraft, allow precise control of orientation and trajectory. But if these are natural vents, if they're places where subsurface ice is exposed and sublimating, then their regularity is hard to explain. Natural cometary activity creates jets from wherever ice happens to be exposed, from cracks, from areas where the insulating surface layer has been eroded away. Those locations are random, irregular, not symmetrically arranged. The enhanced images also show what might be surface texturing, small-scale roughness, or patterns that are at the limit of what high-rise can resolve. Some areas appear smooth, almost polished. Other areas show fine-scale structure that could be impacts, erosion, or possibly designed surface features. The contrast between smooth and textured regions is sharp, with clear boundaries rather than gradual transitions. Natural processes typically create gradual changes. Weathering, erosion, impact processing, these affect surfaces over large areas with smooth transitions between different zones. Sharp boundaries between distinct surface types suggest either unusual geological history or artificial construction. Avi Loeb, who has been one of the most vocal advocates for keeping the artificial hypothesis on the table, has issued statements about the new images. He notes that while none of the visible features definitively prove artificial origin, the cumulative effect of multiple regularities, the cylindrical shape, the linear surface features, the regular spacing of possible vent structures, the unusual spectral and thermal properties, creates a pattern that's difficult to explain naturally. He's calling for additional observations, for more detailed spectroscopy, for thermal mapping at higher resolution, for any data that could help distinguish between the exotic natural object and artificial probe scenarios. The response from other scientists has been mixed. Some agree that the images show features worthy of serious investigation, and that dismissing the artificial hypothesis prematurely would be unscientific. Others argue that we're seeing pareidolia, the human tendency to see patterns and structure where none exists, that we're interpreting ambiguous features through a lens of expectation rather than objective analysis. They point out that image processing can create apparent features that aren't real, that artifacts of compression or enhancement can look like structure, that without ground truth we can't be certain what we're really seeing. But here's what's undeniable. These images show an object unlike any comet or asteroid we've studied in detail. Even if every feature has a natural explanation, even if this is just an extremely unusual but entirely natural body, it represents something new, something that challenges our understanding of what's possible in natural solar system formation. And if any of the features are actually artificial, if even one of those regular patterns or symmetric structures or unexplained thermal signatures is evidence of technology, then we're looking at proof of extraterrestrial intelligence in the form of a probe or craft that has entered our solar system. The images have been released with minimal commentary from NASA. The official statement describes them as high-resolution observations of the interstellar object 3I Atlas captured during its passage near Mars, providing data for scientific analysis of this unusual visitor to our solar system. There's no speculation about artificial origins, no discussion of the regularities and patterns that are so obvious in the images, just factual description of what was observed and when. This restraint is either appropriate scientific caution or deliberate understatement of something extraordinary, depending on your perspective. International reaction has been swift. The European Space Agency has issued statements praising NASA for releasing the data and announcing that ESA facilities will be conducting their own analysis. China has made similar announcements through its space agency, noting that Tianwen also captured images during Atlas's Mars passage and that comparative analysis between different viewing angles will be valuable. Russia's space program has indicated they're redirecting observation assets to gather additional data on Atlas as it continues through the solar system. The scientific community is mobilizing for intensive study. Research teams are forming specifically to analyze these images, to extract every possible piece of information, to test hypotheses against the visual evidence. Papers are being written, submitted to journals, posted to preprint servers. Conferences are being organized. The largest coordinated scientific effort since the early days of COVID research is focusing on understanding what Atlas is and what these images mean. But beyond the scientific analysis, there are broader implications being discussed in government offices and military briefings. If Atlas is artificial, if it's a probe from another civilization, then its presence in our solar system raises profound questions. Where did it come from? How long has it been traveling? What is its mission? Is it autonomous, following programming from long ago? Or is it controlled, receiving instructions from somewhere, reporting back to its creators? Does it pose any threat? Does it offer any opportunity? How should humanity respond? These questions don't have answers yet, but the release of these images, the visual evidence of something extraordinary orbiting through our solar system, makes the questions urgent in ways they weren't before. When Atlas was just unusual sensor readings and spectroscopic anomalies, it could remain abstract, distant, theoretical. But images are different. Images are concrete. They show reality in ways that numbers and graphs don't. And the reality shown in these images is that something very strange is moving through our cosmic neighborhood. The public reaction, as these images spread beyond scientific circles into mainstream media and social networks, is likely to be intense. People will see these photographs. They'll see the regular features, the cylindrical shape, the patterns that suggest structure, and they'll ask the obvious questions. Is this a spaceship? Is this evidence of aliens? Are we being visited? The answers aren't clear, but the questions are now impossible to avoid. Educational institutions, religious organizations, cultural leaders, they're all preparing for the conversations that will follow from public awareness of these images. How do you contextualize the possibility of extraterrestrial technology? How do you help people process information that challenges fundamental assumptions about humanity's uniqueness? How do you maintain social stability while acknowledging that we might not be alone? The psychological impact is already visible among those who've studied the images in detail. There's a sense of awe, of witnessing something historic, of standing at a threshold. But there's also anxiety, uncertainty about what this means for the future, concern about how the situation might develop. Mental health professionals are noting increased stress levels among people working closely with Atlas data. recommending support systems and coping strategies. Economic analysts are beginning to model the potential impacts of confirmed artificial origin. Markets are already showing volatility around space-related sectors. Defense contractors are seeing stock price increases. Traditional resource companies are seeing uncertainty as investors question long-term valuations in a world where the entire human paradigm might be shifting. Economists are warning about potential disruptions, but also about opportunities, ways that new knowledge or technologies could drive economic growth if managed properly. The military implications are being reassessed in light of the visual evidence. If Atlas is a spacecraft, what does that tell us about the capabilities of whoever built it? The size alone is impressive. A 400-meter-long cylinder isn't a small probe. It's a substantial craft, large enough to contain significant equipment, possibly crew or passengers, if it's designed for beings that require physical space. The technology required to construct something this size and send it on an interstellar journey exceeds anything humanity can currently achieve by vast margins. Defense planners are considering scenarios. If Atlas is reconnaissance, what happens after it completes its mission? Does it report back somehow? Does something else follow? If Atlas is a vanguard, what might come next? These aren't questions based on concrete threats, but they're questions that military strategists are trained to ask. Hope for the best, prepare for the worst. Assume competence and capability in potential adversaries. Don't be caught unprepared. But alongside the military caution, there's also diplomatic preparation. If Atlas represents an opportunity for contact, for communication, for relationship with another civilization, humanity needs to be ready to engage constructively. Linguists, anthropologists, philosophers, diplomats are being consulted about how to approach potential interaction with fundamentally alien intelligence. What values might be universal? What concepts might bridge the gap between species that evolved under different stars? The theological discussions are perhaps the most profound. Religious communities worldwide are grappling with what it means if we're not God's only creation, if intelligence exists beyond Earth, if the cosmos is populated with other conscious beings. Some theological frameworks accommodate this easily, seeing it as confirmation of divine creative abundance. Others struggle with how to integrate this possibility into traditional teachings. Religious leaders are being called upon to provide guidance, to help their communities understand and accept a reality that might be vastly different from what was imagined. Artists, writers, filmmakers are already incorporating these images into their work. Science fiction is becoming science fact. Stories that were imaginative speculation are suddenly relevant to current events. The cultural impact of these images will be lasting, will shape how humanity sees itself and its place in the cosmos for generations. We're witnessing the moment when human civilization moves from thinking of itself as alone to recognizing that we might be part of a larger cosmic community. The images also raise practical questions about observation and study. Atlas is moving away from the inner solar system now, heading outward. The window for detailed observation is closing. What additional data can we gather before it becomes too distant for high-resolution imaging? What questions need to be answered urgently? What experiments or observations could definitively distinguish between natural and artificial origin? Scientists are racing against time and geometry, trying to extract maximum information while Atlas is still accessible to our instruments. There are proposals for sending a probe to intercept Atlas, to conduct close-range observations, possibly even to attempt soft contact or sample collection. But the challenges are immense. Atlas is moving fast. Matching its velocity and trajectory would require a mission designed specifically for that purpose, launched with precise timing, using technologies that are at the limit of current capabilities. The cost would be enormous, the risk of failure high, but the potential scientific return, the possibility of confirming whether Atlas is natural or artificial through direct inspection, is making some space agencies seriously consider the option. International cooperation would be essential for such a mission. No single nation has the resources or capabilities to mount an interception mission on short notice. But collaboratively, pooling resources and expertise, it might be possible. Discussions are already happening at high levels about whether such cooperation could be arranged, whether nations that often compete could unite around this shared scientific goal, whether the political will exists to commit vast resources to studying Atlas up close. The coming weeks will be critical. More analysis of the released images will yield additional insights. Other observations from different instruments will provide complementary data. The astronomical community will debate interpretations, test hypotheses, work toward consensus, or at least toward clearer articulation of the competing theories. And throughout this process, the images will remain as evidence, as visual documentation of something extraordinary, as the spark that ignited humanity's most profound questions about what else might be out there among the stars. NASA has released the images of 3I Atlas. They're high resolution, they're detailed, and they show features that are difficult to explain, difficult to ignore, difficult to fit into comfortable categories of natural phenomena. Whether Atlas is an extremely unusual natural object or evidence of extraterrestrial technology, these images mark a turning point. They're proof that our solar system contains mysteries we're only beginning to unravel. They're evidence that the cosmos is stranger than we imagined, and they're a reminder that humanity's journey of discovery is far from over. The images are public now, the world can see them, and the questions they raise about what Atlas is and what it means will shape human thought and culture for years to come. Let me dive deeper into the specific technical details that are causing so much discussion among researchers. When image analysts apply edge detection algorithms to the photographs, when they use computational techniques to identify boundaries and discontinuities in surface features, they're finding patterns that are statistically unusual. Edge detection is a standard tool in image analysis used to identify where brightness changes sharply, where one surface ends and another begins. On natural objects like asteroids, edge detection typically reveals chaotic patterns, random distributions of brightness changes corresponding to irregular surface topography. On the Atlas images, edge detection reveals organized patterns. The linear features align with high statistical significance. The circular vent structures show up as nearly perfect circles, which is geometrically improbable for natural formations. The rectangular panel features have edges that intersect at close to 90-degree angles. These are the kinds of results you get when analyzing images of manufactured objects, not natural ones. Several independent research teams have now performed these analyses, and they're all finding similar patterns. The rotational characteristics of Atlas add another piece to the puzzle. Observations over time show that Atlas rotates with a period of approximately 3 hours. This rotation is remarkably stable, showing very little wobble or precession. Natural objects in space, especially elongated ones, typically tumble chaotically unless they've been tidally locked by gravitational interactions with a planet. Free-floating asteroids and comets usually have complex rotational states, tumbling around multiple axes with rotation periods that change over time as outgassing or impacts impart angular momentum. Atlas's clean, stable rotation around a single axis is unusual. It's the kind of rotation you'd expect from an object with internal mass distribution carefully designed for stability, or from an object with active attitude control maintaining its orientation. Natural objects can occasionally have relatively stable rotation, but it's rare, especially for objects with the elongated proportions that Atlas displays. The probability decreases further when you consider that Atlas has been experiencing asymmetric outgassing, which should be imparting torques that destabilize its rotation. The lack of visible impact craters is also noteworthy. Objects that have traveled through interstellar space for potentially millions of years should show evidence of micrometeorite impacts. Space is not completely empty. There's dust, there are particles, there are small objects that occasionally collide with larger ones. Over long time scales, these impacts create a characteristic pockmarked surface texture. Every asteroid and comet nucleus we've observed up close shows this impact history. In the Atlas images, even at 30-meter resolution, where large craters should be visible if present, the surface appears relatively smooth. There are no obvious large impact features. This could mean the surface is young, that it's been recently resurfaced by some process that erased previous craters. For a comet, sublimation of ice can resurface the nucleus, covering old craters with fresh material. But Atlas shows relatively little active outgassing for its size, not enough to explain complete surface renewal. Alternatively, the lack of visible craters could indicate a surface that's harder or more resistant to impact than typical cometary material, possibly metallic or composite materials. Some researchers have noted what appear to be reflectivity variations that correlate with the linear features and possible panel boundaries. When you measure how brightly different parts of the surface reflect sunlight, there are systematic differences. Some sections are more reflective, some less so. The boundaries between these reflectivity zones align with the linear features visible in the shape. This is consistent with a modular construction where different surface sections are made of different materials or have different surface treatments. For a natural object, you'd expect reflectivity variations related to composition variations, where different minerals or ice types have different optical properties. But those variations are typically patchy, irregular, following the chaotic mixing processes that occurred during accretion and impact processing. The organized reflectivity pattern on Atlas, with variations that follow geometric boundaries rather than random distributions, is another feature that's hard to reconcile with natural formation. The thermal infrared data is being reanalyzed in light of the high-resolution images. Previous thermal observations showed temperature distributions that didn't perfectly match solar illumination. Now, with precise knowledge of surface geometry from the high-rise images, researchers can create detailed thermal models, predicting exactly how warm each part of the surface should be based on sun angle, surface orientation, thermal properties of materials. When these models are compared to actual thermal observations, there are discrepancies. Some areas are warmer than models predict, suggesting internal heat sources or thermal regulation systems. Some areas are cooler than predicted, suggesting active cooling or highly reflective surfaces that reject solar heating more efficiently than natural materials. These thermal anomalies are subtle, just a few degrees in most cases, but they're systematic and consistent across multiple observations. They suggest Atlas is not a passive object in thermal equilibrium with its environment, but something with active thermal management. The spectroscopic observations are being revisited with new attention to detail. When you look at how Atlas reflects light at different wavelengths, there are absorption features, specific wavelengths, where less light is reflected. These features can identify what molecules or materials are present on the surface. Atlas shows some standard absorption features consistent with organic compounds and silicates, but it also shows features that don't match well with known materials. Some spectroscopists have suggested these unidentified features could be from highly processed organic materials, tholins created by radiation exposure over millions of years. Others suggest they could be from minerals that are rare in our solar system but might be common in the stellar system where Atlas originated. And some are beginning to quietly suggest they could be from artificial materials, polymers, or alloys that don't occur naturally, substances created through industrial processes rather than geological ones. The particle emission that's been observed from Atlas is also being reconsidered. The jets that optical telescopes have captured, the material being released from those circular vent-like features, what is its composition? Spectroscopic analysis of the jet material shows primarily water vapor and dust, consistent with cometary outgassing. But the velocity of the ejected material is unusual. It's being expelled at higher speeds than you'd expect from simple sublimation of ice heated by the sun. Sublimation-driven jets typically have velocities of a few hundred meters per second, material being expelled by pressure far. The analysis continues, with researchers worldwide examining every detail, testing every hypothesis, working to understand what these images truly reveal. The images have been released, the debate has begun, and humanity stands at the threshold of potentially answering one of our oldest questions about whether we're alone in the universe.